Hello, and welcome to this lesson on precision DACs. Today we will explain the topic of DAC calibration while illustrating how best to eliminate the inherent errors normally associated with DACs in practical applications. Why is DAC calibration even needed? As any DAC used in a real system is obviously non-ideal, each will exhibit some level of overall error, of which a portion can easily be calibrated out. Such an error is comprised of 5 typical inherent components as follows: zero scale error, full scale error, integral nonlinearity error or INL, offset error, and finally gain error. In the course of this presentation, we will define each component and its effect, as well what can and cannot be calibrated out. Please also note that any observed DAC error can also be influenced by signal chain components within the system, but external to the DAC itself. As such, errors are beyond the scope of this lesson, and they will not be discussed further in this presentation. Before we get into the specifics of each error, let's first look at what output function you would expect from an ideal DAC. In an ideal world, your ideal DAC, in this case a voltage DAC, would simply exhibit a perfectly linear output function as shown on the left, where at an input code of 0x0, your output voltage would simply be 0 volts, while an input code of, say, 0x7 would provide an output voltage, in this case, of 4.375 volts, which provides for a perfectly linear function. Next, we will define each error and its impact. As previously noted, every DAC possesses several inherent errors, 2 of which are zero scale error and full scale error. Zero scale and full scale errors are inherent localized endpoint errors that don't affect the entire transfer function or the DAC's actual performance. Such errors are static errors that occur when a converter is converting static DC signals. While zero scale and full scale errors cannot be calibrated, the variables associated with zero scale and full scale errors are well documented with each datasheet. Considering that the remaining curve between the two endpoints of any DAC output function is non-ideal, and that it does deviate from an ideal linear transfer function curve, this deviation, the third inherent DAC error, is called integral nonlinearity, or INL. INL is a typical performance specification for all DACs, representing the measure of deviation between the ideal output value and actual measured output for a particular input code. While INL cannot be calibrated, each DAC datasheet highlights the deviation as a specified range. For example, the DAC 60501 has a specified INL of plus or minus 1 LSB, maximum at 16-bit resolution. Next, we will talk about gain. Before we talk about the 2 remaining inherent DAC errors that relate to any DAC's output function and resulting gain, let's first define this gain. Gain is essentially the slope, m, of a DAC's output function, expressed on datasheets as a percentage of full-scale range, or simply percent FSR. This slope, measured between the maximum point on the illustrated function, x2, y2, and the minimum point, x1, y1, can be expressed as the slope m equals y2 minus y1 divided by x2 minus x1. Next, we will look at the errors that actually impact the resulting DAC function and its gain. Now that we understand gain, let's take a look at the 2 remaining inherent DAC output function errors: offset error and gain error. Offset error represents the actual offset of the starting point of the DAC's output function from the ideal function. Gain error, on the other hand, represents the shift of the DAC's output function endpoint from the ideal function. Unlike the three previously defined errors, both offset and gain errors can be calibrated, which will be explained in the next slide. When taken together, offset error, gain error, and INL are the three key inherent variables that affect a DAC's overall precision. Together, these variables also define what is called a DAC's total unadjusted error, or TUE. TUE is the standard method of calculating and expressing the total DC error of a DAC. The equation used to calculate TUE is as follows. TUE equals the offset errors squared plus the gain errors squared plus the INL errors squared, all to the square root. As previously noted, while INL cannot be calibrated, it is defined within any DAC datasheet. And as offset and gain errors can be calibrated, we will now see how calibration of these two inherent errors can positively affect our overall TUE. Calibration is done in the linear region of the DAC, because this is where the offset and gain errors are actually measured. DAC gain error and offset error are calculated as follows. As each DAC datasheet specifies the actual codes at which each measurement is taken, this makes it very easy to calculate the actual gain and offset errors based on the noted equations, where slope m is the slope of the actual output function, and n equals the resolution of the specific DAC. Again, gain error is measured in percent full-scale range, or FSR, while offset error is measured in volt units. Next, we will discuss actual calibration of a DAC. The easiest way to do calibration of a DAC is by using a two-point approach, as follows. Take the points on either end of the linear region of the output function, where the offset calibration code is the difference between the measured and ideal Y values at the low code, while the gain calibration ratio is calculated from the slope of the measured line. Finally, you can put these two calculations into the new code equation to get the adjusted code value that should be used. You can also program this routine into your digital controller, which can often drastically decrease your system total unadjusted error, but remember that using this method could address a code that is out of range of your controller, so please make sure your programming scheme takes this into account. Next, let's look at an example where gain error and offset error are calibrated. Let's take a look at the DAC 8562, which is a 16-bit 0 to 5 volt output DAC. Listed here are the INL, offset, and gain errors for the DAC 8562, as listed in the datasheet for both typical and maximum values. Please note that we needed to convert the spec units into LSBs if it was not already specified that way. Using the max values from the datasheet for each error and plugging them into the TUE equation, the DAC 8562 then results in a plus or minus 112 LSBs of total unadjusted error. This is a rounded number. When using typical spec values from the datasheet, the error drops to plus or minus 15 LSBs. Now let's see what happens after we calibrate. Once correctly calibrated, both the offset and gain error terms of the TUE equation are negated, leaving only INL to affect the overall TUE calculation. In this case, it reduces the typical TUE to simply plus or minus 4 LSBs, with a maximum of plus or minus 12. Please note that while this method may introduce about 1/2 of an LSB of offset error because of rounding in the adjusted code calculations, such minor gains from calibrating are generally well worth the result of so dramatically reducing the overall TUE. In conclusion, in this lesson we defined and discussed the fundamentals associated with the 5 inherent errors associated with DACs and how calibration can be affected. Further, we defined the 5 inherent errors of zero-scale error, full-scale error, integral nonlinearity error, or INL, offset error, and gain error. That zero-scale and full-scale errors are inherent, localized endpoint errors that don't affect the entire transfer function or the DAC's performance, and that while zero-scale and full-scale errors cannot be calibrated, their error variables are defined and documented within each product datasheet. That integral nonlinearity error, or INL, is an inherent error for each DAC that can also not be calibrated but is defined in each datasheet. That offset error and gain error do impact the desired output function of a DAC, but can be easily compensated for through calibration. That the DAC's total unadjusted error, or TUE, is composed of INL, offset error, gain error, whereby once offset and gain errors are calibrated out, you are simply left with a TUE composed of just the DAC's INL. Finally, that a DAC's total unadjusted error, or TUE, is composed of integral nonlinearity error, or INL, offset error, and gain error. Now let's complete a short quiz to check what we've learned today. Question 1. Zero-scale and full-scale errors are endpoint errors that do impact a DAC's output function or its performance. The answer is B, or false. Zero-scale and full-scale errors are outside the output function itself. Question number 2. Total unadjusted error, or TUE, is comprised of which components? The answer is E, A, C, and D. This includes offset, INL, and gain errors. Question number 3. Following calibration, remaining TUE is primarily comprised of INL. True or false? The answer is A, or true. Thank you for watching this video on the calibration of precision DACs. To watch our other DAC training videos, please go to the ti.com/PDAC landing page as hyperlinked above.